I2C is a multi-master, single-ended serial communications bus invented by Philips. It's primarily used to connect low-speed peripherals to motherboards, embedded systems, cell phones, or other electronic devices. Here is an I2C signal with a baud rate of 125 kHz and the data string Rigol. Now let's use a Rigol oscilloscope to trigger and decode the incoming signal. Connect probe 1 to the I2C source clock and ground to channel 1 of the oscilloscope. Use probe 2 to connect I2C data and ground to channel 2 of the oscilloscope. Press Auto. The scope now adjusts the vertical and horizontal parameters automatically, but notice that the waveform is not triggering stably. Now adjust the time base to 100 microseconds per division. Choose the I2C trigger and set the trigger conditions using the following. Set the trigger type to I2C, set channel 1 to source clock, channel 2 to source data, trigger condition is set to start, and trigger mode is auto. Now we can adjust the level of channel 1 and channel 2 to get a stable trigger. Now let's configure the decoding. Press Decode, set the decode type to I2C, and turn on the bus function. Set the source clock to channel 1, source data to channel 2, set the format to ASCII, and adjust the threshold of source clock and source data. Now we can see the data, Rigol, on the screen. Sometimes we need to have the scope set on a large time base, but then we cannot see the decoded data clearly. Enabling the event table can help us to see more data and corresponding time, position, and error information. When you enable the event table, all the data can be seen more clearly. You can also export the event table data to an external USB drive. Here are some key points when decoding I2C signals. You want to choose the right time base and vertical scale for your signal. Set the trigger conditions to match the signal encoding. Set the decoding conditions to match the signal encoding. Open the event table and you can get more data, as well as store that in USB. Thank you.